Next, we have classical atom size. It's really hard to define what an atom is because the electrons are always in motion. We like to draw them in these nice orbital kind of pictures, but remember, electrons can be treated as waves, and they can really be anywhere. 90% of the time it's here, but these electrons are in waves, and these waves kind of move, and it could be over here. So it's really hard to define the classical atom size. Traditionally, the classical atom size has been, okay, if I have two of these atoms that are next to each other, what is half of the distance between the nucleus? That's generally how they define the classical atom size. That's also referred to as the non-bonding atomic radius. Okay, so we have some things with that. You can estimate the bond length for certain things based on the idea of effective nuclear charge. Here's a couple of estimates that you have here in terms of picometers. And like I said, it's the sum of, hey, if I have two hydrogens, okay, if I have two hydrogens together, that's the distance between the two of them. So if I was looking at what the bond length of this, or what this hydrogen would be, I take it divided by 2, and that would be the size of a hydrogen atom. Quantum size. Whenever you look at an atom in terms of a quantum atom, there is no defined boundary. The electron can be anywhere. I mean, this is the atom, the nucleus is right here. Most of the time the electrons are here, but the electrons can be all the way in Thailand for some reason. Okay, so because of that, you can't really define a quantum atom size. Instead, what you do is you talk about an atom in terms of probabilities, and in which case the electron probabilities must equal 1, because the electron has to be somewhere in relation to that atom. Atomic radii. So the atomic radii increases as you move down the periodic table, and it increases from right to left. So it's kind of an interesting pattern that you've got there. So we're going to look at that in terms of Coulomb's law. If you look at atomic radii and the clench, more protons equals a greater attraction to the nucleus. Okay, a lot of times when we talk about atomic radii, we talk about the isoelectronic species. Isoelectronic species are atoms that have the exact same number of electrons but varying number of protons. Okay, and so here's the example that we have here. The example that we have here is O2 minus, F minus, neon, Na plus, and Mg2 plus. Okay, those are isoelectronic species because they all contain the same number of electrons. Neon has 10 electrons and 10 protons. Okay, fluorine has 9 protons and 10 electrons because it's F minus. O2 minus has 10 electrons and 8 protons. Sodium has 10 electrons and it has 11 protons. Magnesium has 12 protons, and once again it has 10 electrons. Now, if you were to look at the relative attraction between these two, remember, the more charge there is, the more they're attracted to one another. So if you have 8p and 10e, there's not a very big attraction between those two, so because of that, the atom tends to be larger. Okay, whenever you have fluorine, you're adding more positive charge, so it's going to pull these 10 electrons in closer, but still not that much. When you get to the idea that you have 12 protons attracting these 10 electrons, it's going to make a significant difference in shrinking that atom. Okay, atomic radii, more electrons equals a greater attraction and therefore a smaller radius, unless another level is added. So once again, it brings up the whole idea of if I have, let's say I have oxygen, and if I just have regular oxygen, and I have neon and I have fluorine. Okay, oxygen or neon's got 10, fluorine's got 9, oxygen has 8 because they're not ions anymore. Okay, 8 protons, 8 electrons, 9 protons, 9 electrons, 10 protons, 10 electrons. The attraction between these two is going to be much, much greater than it is between these two than it is between these two. So because of that, oxygen tends to be larger. Now, once you get to the fact that you get to the next level up, which is sodium, and you say 11 and 11, they say, well, sodium's got to be smaller then because that's going to be an even greater pull. And it's not, because at this point, oxygen, fluorine, and neon work on 2 orbitals. This orbital and then this orbital. When you get to sodium, you're adding a 3rd orbital. When you add that 3rd orbital, you're greatly increasing the atomic radii because you're significantly increasing the distance away at that point. Ionic radii, generally ionic radii is determined by comparison with the electric crowd it emulates. So if you were to look at lithium, you would compare lithium to helium. Now the difference is that helium has 3 protons and 2 electrons because it's an ion, and this one has 2 protons and 2 electrons. So if you were to look at this, you would say that this would have a greater attraction than this, and therefore the lithium ion, although it's very similar in size to helium, is going to be slightly smaller because it's going to have a greater attraction. So now we need to talk about the idea of ionization energy. We've already explained atomic radii and ionic radii in terms of Coulomb's law and effective nuclear charge, but now we need to look at the idea of ionization energy. Now, just as a review, ionization energy is the energy that's required to remove an electron from an atom completely. So it depends on the positive charges, the negative charges, and the distance between. In other words, it depends on Coulomb's law. And it's interesting that you see a very similar pattern to effective nuclear charge as you see with ionization energy. So if you were to look, this is the ionization energy of hydrogen. This is the ionization energy of helium, and then so it goes up, and then you see a very significant drop. Lithium drops way down. Then you see an increase. You see an increase, kind of a little drop right there, and we can talk about those drops in just a second. But a general increase and then a drop, a general increase and then a drop, a general increase and then a drop, which is very, very similar to what you see for effective nuclear charge. Now let's talk about why. If you were to look at it in terms of effective nuclear charge, the reason why you see such a precipitous drop is you are going from helium, where you've got 2 electrons, and the effective nuclear charge is 2, you're adding a significant amount by adding a 3rd electron. Yes, the effective nuclear charge goes from 2 to 1, so we are decreasing the overall pull because of the charge, but you're also, look at this big difference in distance. The difference in distance is you're increasing the distance. Now remember, Coulomb's law says that the force that attracts the two is equal to Q1, Q2 over d squared. So any change in the distance is going to have a dramatic impact on the amount of energy or force required to pull something apart. And you can start to see these in the trends. Now, this makes its way in terms of ionization energy. You can see that you can ionize something multiple times. And you can see this right here. This is a big question that you tend to see on the AP exam because there tend to be questions about data, and they show this data to ask questions about. So you see the element, you see the energy for the first, second, third, fourth, fifth, sixth, and seventh ionization energies. Now the general thing that you would expect to see is as you remove an electron, you make it more difficult to remove another electron. Okay, and that just has to do with the fact that whenever you remove an electron, it's going to have the opportunity to shrink just a little bit, and so it's going to be more difficult to remove that second one. So the general idea is that you would see an increase in the energy, and you definitely see that for sodium. Look at that giant increase between the first and the second. But now, if you were to look at magnesium, you see a much smaller increase with the second one, and then a giant increase with the third one. For aluminum, you see a slow increase for the first, second, and third, and then you see a giant increase for the fourth. Well, let's try and explain why. If you were to look at sodium, you have your positive nucleus. You have the first orbital, which has 1, 2 electrons in it. You have the second orbital, which has 1, 2, 3, 4, 5, 6, 7, 8 electrons in it. And then you have the third orbital, which has 1 electron in it. So the amount of energy required to remove the first electron is that 496. So I take that first electron out, and now what I'm doing is I'm having to move to an inner orbital where these electrons are not only have a high effective nuclear charge, okay, the effective nuclear charge is as high as it can be, but also they are much closer than this original electron because I'm going from the third energy level to the second one. Removing one from the third energy level is much easier than removing one from the second. So now, let's look at it for another element. If you were to look at it for magnesium, magnesium originally starts off with 2 electrons in its outermost energy level. So removing the first one is relatively easy. Removing the second one is relatively easy. But then I'm trying to, once again, remove an electron from the inner orbital level. And that tends to be very, very difficult. So you see this pattern continue. First one, second one, third one, fourth one, all of these are in the 3s orbital, but when I jump up to that fourth orbital, that's where it gets very, very difficult. So the first ionization energy trends, ionization energy decreases as you move down the periodic table. The reason why it decreases as you move down the periodic table is as you move down the periodic table, you're adding layers or increasing the distance that you're moving away from the atom. Okay, generally ionization energy increases as you move across the periodic table. The reason why it increases as you move across the periodic table is the effective nuclear charge is increasing. So the effective nuclear charge starts at 1 and then goes to 2 and then 3 and then 4 and then 5. So it takes more energy to pull them away because they're more attracted to another at that point. Electronegativity is the ability of an atom to capture an electron to gain access to the positive nucleus. And once again, it depends on the same things that we're talking about in terms of Coulomb's law and effective nuclear charge. Electron affinity is the same thing. It's the measure of an attraction for an electron. It's the amount of energy released as an electron is added. And so once again, it's the whole idea of what is the pattern between Coulomb's law and effective nuclear charge and electron affinity. Okay, we tend to deal with electron negativity whenever we're talking about bonding, and electron affinity whenever we're whenever we're referring to an atom by itself obtaining an electron, so ionization, those sorts of things. So electronegativity increases as you move down the periodic table. Okay, so we see increasing this should say as you move up the periodic table. Okay, electronegativity goes up as you go this way, and electronegativity increases as you go to the right. And the reason why is you're talking about access to the positive nucleus. Okay, that's what's happening. So for electronegativity, you're trying to bring an electron in. Well, as you go up the periodic table, here's my positive nucleus. Well, if I have, let's say, 3 orbitals, okay, if I have 3 orbitals, it's very difficult for an electron here to access the positive nucleus. But if I were to take this orbital away, well, now it's a whole lot easier because I've only got 2 orbitals to deal with. And if I were to go here, now it's a lot easier because I only have 1 orbital to deal with. So as you go up this table right here, you're increasing the electronegativity because you have better access to the positive nucleus. Now, as you move across the periodic table, you're increasing the positive charges that are in the nucleus. The positive charges are going to have a greater impact on this electron right here because the bigger the positive charge, the more electrons are going to be attracted to it because you are increasing the effective nuclear charge. Now this trend excludes noble gases. Noble gases, remember, are perfectly satisfied. So when we say it increases from left to right, it does so excluding the noble gases. Here's an example. It says, this is a tough one. It says, under what circumstances might helium have a greater electronegativity than fluorine? And you look at fluorine as the most electronegative of all the elements. And the reason why it is because it has a positive charge, and it has only 2 levels, and it has 1, 2, 3, 4, 5, 6, 7, and let's add the s orbital there, 8, 9. It's got 9 electrons. So it has an effective nuclear charge of 9 minus 2, which is 7. That's an extremely high effective nuclear charge. It only has 2 orbitals to contend with. So it has access to a very, very positive nucleus. And so that's what makes it have the greatest electronegativity. So the question is how could I make it so that helium has a greater electronegativity than fluorine? And the only way that I can think of is if you remove an electron. If you had helium that had a +1 or even a +2, the effective nuclear charge of helium would be 2. Okay, so the effective nuclear charge is smaller, yes, but the effective nuclear charge of helium is greatly helped by the fact that it only has 1 orbital. Not only does it only have 1 orbital, but it only has 1 electron that could possibly interfere with an external electron. So the only way that you're going to have a greater electronegativity than fluorine for helium is if that helium is an ion. And helium is very, very difficult to ionize. Next it says, describe why magnesium and copper have the same atomic radius. Okay, remember, atomic radius is determined by Coulomb's law an effective nuclear charge. So if you wanted to look at this, you have to look at their relative positions on the periodic table. So the first thing you want to look at is where is magnesium and where is copper on the periodic table. So let's pull up our periodic table, and when we do that, we see that magnesium is 3s2, so which means that it has 10 shielding electrons, and it has 12 is the atomic number. So the effective nuclear charge is 2, and it has 3 orbitals to contend with. Okay. Copper, on the other hand, copper, if you were to look at it, is in the 4th column, and it has, once again, it's got 18 shielding electrons, but it has an effective nuclear charge of 11. So that right there shows that copper has a greater effective nuclear charge. So there's a greater positive pull on a valence electron. But magnesium has 3 energy levels. Copper has 4. So even though this one has 3 energy levels, those energy levels are relatively spread out because the effective nuclear charge is fairly small at positive 2. Copper, on the other hand, has 4 orbitals, 2, 3, 4, that are relatively spaced together because of its rather high effective nuclear charge of 11. So they're not the exact same, but it shows you how two elements could have approximately the same atomic radius, even though they're in very different periods and very different rows. Periodic trends. Only the noble gases are found as monatomic atoms in nature. Elements are divided into nonmetals, metals, and metalloids. Now, generally speaking, we refer to metalloids as the stair-step ones, starting with aluminum and working our way diagonally across the periodic table. Those tend to be things like our semiconductors. Nonmetals are to the right of the stair-step, metals are to the left. The only one that's weird is hydrogen. Okay, when you look at the periodic table, depending on what you're looking at, sometimes helium should be here because it's an s orbital. Sometimes hydrogen should be here because it's a nonmetal. They're the only two ones that are weird. Everything else, metals to the left, nonmetals to the right. Properties of metals: they conduct heat, they conduct electricity, they're malleable, which means they can be pounded into thin sheets, they're ductile, which means they can be drawn into thin wires, they're solids at room temperature, they are very, very easy to ionize, they form cations when they do, which means that they are positive metal ions, and they form ionic bonds with nonmetals. They tend to be basic, so if you were to add them to acids, they tend to neutralize them. Okay. On the other hand, you have nonmetals. They don't conduct heat. They don't conduct electricity. They tend to be gases at room temperature. Some of the bigger ones are liquids. They have high ionization energy. It's very difficult to remove one because their effective nuclear charge is much higher. They form anions, which are negative. They form ionic bonds with metals, and they form covalent bonds with each other. Okay, they're nonmetals and they tend to be acids. The metals themselves, they can form what are called metallic bonds with each other, which are very, very different than the covalent bonds that are formed with nonmetals. Metalloids are somewhere between the metals and nonmetals in all properties. That's why they tend to be semiconductors in heat, semiconductors in electricity, those sorts of things. Alkali metals, you see, are group 1. They're soft, metallic, lustrous, and they're very reactive. Alkaline earth metals, group 2, soft, metallic, dull, reactive. Transition metals, group 3s, hard, metallic, lustrous. They tend to make colored solutions, like copper makes blue or green, depending on what it's paired with, and iron is red or orange. They tend to be conductors. Halogens halogens are obviously nonmetals. They're group 17. They tend to be gases at room temperature, except for I think this last one right here is not. Oh, and bromine tends to be a liquid. They're highly reactive with nonmetals, and they're very, very lethal to organisms. Noble gases, non-reactive gases. So what element in halogens has the largest atomic radius? So if you were to look at this by saying halogens, we've limited it to this particular column. So which element has the largest atomic radius? If you're in the same column, they all have the same effective nuclear charge. So because of that, you would look at the one that's the lowest on the periodic table because it would have the most layers, and the one that has the most layers is At. So that would be our largest atomic radius. which elements would have the same chemical properties of calcium. If you were to look at calcium, calcium is in group 2 of the periodic table. So you can name anything in group 2 of the periodic table, which would include beryllium, magnesium, strontium, barium, radium. The ones that are closer to calcium would tend to be more similar, so those would be magnesium and strontium. When you get really small or really big, sometimes they react much more strongly or much less strongly based on effective nuclear charge.